Hi everyone, welcome to the 1.14 notes. Today's notes are talking about how we can connect infinite limits and vertical asymptotes. So I want you to look at these three graphs and notice that they're all limits that are approaching infinity. And so look at the first one, the limit as x approaches 0 of f of x. That's going to be infinity because as we are getting closer and closer and closer to 0, we are going up forever. So Desmos doesn't always add arrows for us, but there are arrows on all of these. This next function, as g of x approaches 3, the left-hand limit approaches negative infinity and the right-hand limit approaches positive infinity. And so while it is an infinite limit, overall the limit does not exist because it's not approaching the same from both sides. And then finally, h of x, as it approaches 4, the function is approaching negative infinity. And so something I want you to notice is in all of those places, whether it is marked or it's not marked, there is a vertical asymptote. So if I look at this very first function, there is a vertical asymptote at x equals 0. We are never actually going to ever touch x equals 0. We're never touching that. And so I could write the equation of my vertical asymptote as x equals 0. In this next one, it is marked. You can tell very clearly that there is an asymptote at x equals 3. And then finally, there's a vertical asymptote on this last one at x equals 4. Even though it's not marked, it does exist there. So there is an asymptote at x equals 4. And so what I want you to notice here is anytime we have an infinite limit, there will be a vertical asymptote that is paired with that. And so we're going to talk about, this is going to be a little pre-calc review, but obviously it was very easy to identify all those asymptotes. Even if it wasn't marked, we kind of know the pattern, what's going to happen. But what if we were asked to find the vertical asymptote of a function without a graph? So if you are looking at a rational function, rational functions are normally where we're going to see the vertical asymptotes. That's just like a function that there's a fraction, there's an x on the numerator and the denominator. What you are looking for is a rational function will have an asymptote where the denominator has a value of 0, but the denominator does not have a value of 0. And that idea of the denominator not having a value of 0 has to do with removable discontinuities. So for example, if I look at this function right here, if I were to plug in x equals 2 to this function, so I want you to look at the denominator, and what you should be thinking about is what numbers would cause the denominator to go to 0. So if I plugged in x equals 2, I would have 2 minus 2, 2 minus 4, and 2 minus 2 is 0, and then 2 minus 2 is negative 2. And so my denominator does go to 0 if I plug in 2, but also so would my numerator. And so this would give me a 0 over a 0, and technically this is my removable discontinuity. And so if you look at the graph at x equals 2, there is not an asymptote at x equals 2, there is a removable discontinuity. And that's because the numerator goes to 0, and so does the denominator. And so it kind of cancels out the asymptote. However, if you were to plug in x equals 4, you would have the numerator going to 2, and then you would have the denominator going to 2 times 0. And so here, this is an example of where the denominator has a value of 0 and the numerator doesn't. And so that means that there's going to be a VA, a vertical asymptote, at x equals 4. And if you look over here at the graph, we see one. We see a vertical asymptote at x equals 4. And so that's what we mean by the denominator has a value of 0 and the numerator does not. So looking at these examples real quick, I want you to think for a second and feel free to pause it. But which of the following has a vertical asymptote at 3? So I'm just going to keep going through it. But if we look at f of x, if I plug in 3, I get 1 over 0. And so there is a vertical asymptote at x equals 3. This next one, if I were to plug in 3, I would get 0 over 0 times 5, aka we'd have 0 over 0. But because the numerator is 0, this essentially gets removed. And so there is no vertical asymptote there's no VA at x equals 3, because while the denominator has a 0, the numerator doesn't. But there would be, this is just asking at x equals 3, but there would be a vertical asymptote at x equals negative 2. This next one, is the same situation as the last one. There actually are no vertical asymptotes at all in this, because if you plugged in 3, these would cancel out, and then you'd be left with x plus 11. So essentially there's nothing besides 3 that's causing a 0 on the denominator. So there's no vertical asymptote at x equals 3, and there's actually none at all. Like there's none in general. And no VAs in general. And then this next one's kind of a weird one, because if you plug in right now, if you were to plug in 0 or 3 on the top and the bottom, you'd have 0, 14, and then you'd have 0 squared. And so you might think, okay, the denominator is 0 and so is the numerator. However, if I were to kind of write out what this means, this is really this function, and so only one of my x minus 3's get removed. There would still be one left over, because there's basically, if you were to plug in 3 here, you almost have, I just did this, but you have 0, 11, but you really have 0 squared. So there's 2 zeros there, and so the numerator 0 only cancels out one of them. And so for this one, there is a vertical asymptote at x equals 3, because there was more than 1 0 on the numerator or on the denominator when you plugged in 3. So removable discontinuity can only cancel out one of them, and so this one there is a VA at x equals 3. Okay, the other example of functions that you will see, so rational functions, you'll see asymptotes, and then logarithmic functions, you'll see asymptotes too. So the domain of a logarithmic function is 0 to infinity. So if you were to plug in the natural log of 0 into your calculator, you would get like an error message. So the natural log of 0 does not exist. And so the vertical asymptote at this one is x equals 0. And then this next one is a vertical asymptote, but it's just with a shift. It got shifted 3 places over. And so this one, the domain is actually -3 infinity. And so this vertical asymptote is at x equals -3. So log functions or other functions, you'll see vertical asymptotes, and then they're not always going to be at x equals 0, because sometimes there can be shifts of the functions, and so that will change where the asymptote is. And all of the shifts that would impact it are inside the parentheses, because the shifts inside the parentheses are what's affecting the x, and it's always like opposite of the way you would think it would be. So that's that one. So for this example, it says let h be the function h of x equaling x squared minus 3x plus 2 divided by x squared minus 4 times the natural log of x minus 4. At what values of x does the graph of h have a vertical asymptote? And so you could go ahead and plug in all of these values, and that would be one way to do this problem. But what I think is easier is to go ahead and see the factors of this function. And so I'm going to go ahead and factor this out. So if I factor this out, I will have x minus 2 times x minus 1 on the top, all over x minus 2 times x plus 2 on the bottom, times the natural log of x minus 4. Sorry, guys. Okay, so going ahead, this factor gets canceled out here. And so plugging 2 into the function does not cause a vertical asymptote, because it's a removable discontinuity. So I'm going to go ahead and cancel all the ones that had x equaling 2 as the answer. And just like that, we know the answer. Like, it has to be C by process of elimination. But I'll tell you more, like, why it has to be C. So basically, if I plug in -2 here, I'll have some number over 0. And then also 4 here would be where the asymptote is because this is shifted over 4 places. And so the asymptote would be happening at x equals 4. So one way you know the answer is because you cancel it out, right? But that is how you would actually determine that. So the x equals -2 is because of this piece right here. And the x equals 4 part is because of the domain of a natural log function. And so if you do x minus 4, you're actually shifting your graph over to the right 4 places. Okay, so those were all pre-calc style questions. All of these questions you could have answered in pre-calculus, but now we're going to switch over to some calculus style questions. And so we'll do example 4. And so it says the values of k of x can be made arbitrarily large. So if you hear the word arbitrarily large, I want you to automatically think infinity. So the values of k can be made arbitrarily large by taking x sufficiently close to 7 but not equal to 7. Which of the following statements must be true? Now, some of these answers could be true, but the question is asking what must be true. And so we'll just go through these. It says k of 7 does not exist. we don't know that. There's nothing here that tells us that it doesn't exist. Right now, what we're basically being told is that the limit as x approaches 7 of k of x equals 8. That is what this language is telling me right here. I don't know that this is true. They would need to tell me specifically that k of 7 does not exist for me to be able to answer that question, because it could always be a situation where it's looking like this, but then it's a piecewise function where they fill in a point somewhere. A value can't equal infinity, so this one is out. A value can't equal infinity. Infinity is not a number. This one says the limit as x approaches infinity is 7, but this is saying that we're taking x sufficiently close to 7, not taking x sufficiently close to infinity. If we are, and we'll do this the next notes we have, but if we're going close to infinity, and I guess this is negative infinity, we're saying that as we go on forever, what is happening to the y values, but that's not what this is asking. So this one's out. So again, by process of elimination, D is the right answer. But if the limit overall, I'll say this real quick before they start talking. If the limit overall is 7 from both directions, oh, never mind.
All juniors, dismiss for math. All juniors, dismiss for math. Thank you.
Okay, sorry. So if the limit overall is infinity, that implies that the left-hand limit and the right-hand limit equal infinity. So if this is occurring, then D has to exist. So if the limit overall is infinity, that means the left-hand limit is also infinity. So that's why D is the answer. Okay, we just have a couple more problems. Example 5 says, it is known that the limit as x approaches -6 of g of x equals negative infinity. Which of the following could be a likely table for g? So this is saying -6, and there's no like left hand or right hand. Like it's not like -6 minus or -6 plus. So that means as I look at this table, from both directions, the numbers should be getting closer to negative infinity, which means we should be noticing the numbers getting smaller and smaller and smaller. So as I look here at this first one, so as we're approaching -6 from the left, these numbers are getting really, really small. As we're approaching -6 from the right, these numbers are getting really, really small too. So right off the bat, we know answer is A, because that fits both conditions. But let's just talk about why the other ones are not correct. So this next one, as we approach -6 from the left, it's approaching negative infinity, but from the right, it's approaching positive infinity. This one's the reverse. As we approach from the left, positive infinity, from the right, negative, and then from the left and the right, it's positive infinity. So those are why those ones don't work. This next one says the function m is continuous at all except x equals 9. If the limit as x approaches 9 of m of x equals negative infinity, which of the following statements must be true? So I'm going to draw a little sketch of this graph based on what that's saying. So that's saying that when we get close to 9, the function's approaching a negative infinity. And it says, doesn't have any left hand or right hand, so that means from both directions. So we're going to use this to help. But there's one other thing I can do to just cancel out some answers. Vertical asymptotes, you always write the equation with x. So a vertical asymptote is always an up and down asymptote. And the equation of vertical lines are written with x's. The equations of horizontal lines are written with y's. And so I can go ahead and cancel out a bunch of these answers that don't correspond. So basically, b can be canceled out because it says x equals 9, and x equals 9 would be a vertical line, and it says it's staying horizontal. And then likewise, I could cancel out c because it says y equals 9, and it's saying vertical, but y equals 9 would be a horizontal asymptote. So those ones can automatically cancel out. We haven't really talked about horizontal asymptotes yet. We'll talk more about that later this week. But if I show you my sketch over here, at x equals 9, if the function is going to be approaching negative infinity there has to be a vertical asymptote. So the answer for this one is D. This totally could be true, maybe, but we don't know that, so I'm taking that out. Okay, the next two questions are really similar to other ones, so I'm just gonna want you to pause it, but I'm gonna go ahead and just circle the answers for you. D. And then try this one too. Pause it. This X shouldn't be here. And the answer to this one is B. So hopefully you were able to figure that out on your own, but if you have any questions about why those ones are the answers, make sure that you come, or you ask during office hours. You can come ask during office hours, but you can also ask during class. So that is the 1.14 notes. Thanks for watching.